All right, so up to now, what we've done is we've basically gone through and just computed our variables, all that stuff, and we've checked our assumptions of MANOVA. We've checked for linearity, homoscedasticity, et cetera, et cetera. So today we're actually going to fit our model and conduct our multivariate analysis, followed by a step-down procedure. So to start, we will be here under macro assessment, just above number 13. So first, let's make the model, and then we'll discuss, what the research question is answering. So when you're fitting a MANOVA model, you fit it very similarly to how you would fit a linear model using your LM function. The only difference is that instead of having some DV regressed on a bunch of IVs, you have multiple DVs regressed on one or more IVs. The way that you tell R that, hey, I need multiple dependent variables is you have to bind them together so that there's basically a matrix of, however many DVs you have is how many columns you would have. So you'll use C bind, and C bind all your DVs together. So we'll say LM and C bind our 3 DVs of education 3.n, job sat 3.n, and job score 3.
I think you've got a typo. And education.
And so if we take this and if we just look at what the C bind itself does, because we haven't used this yet, if I run just this C bind with our 3 variables, I still have a typo.
You have a point between score and the U in education.
How did you do that thing with the DF dollar
Good God.
Do we have to run everything we've done up to this point? Is that right?
Yeah.
Okay.
Because job score 3 is not a dot .n. Haha, there we go. So the all it's doing is it's taking the 3 columns of our DVs and making it as one matrix of values. As far as how I did that DF thing on Mac's multi-spot editing is holding Option Command and clicking wherever, and you can have as many cursors and type simultaneously across lines. I don't know what it is on Windows. You can look up multi-line editing and probably find the keyboard shortcuts. But anyway, so this is all our C bind is doing. This is what we're telling this collectively is our DV in our linear model.
For some reason, I'm struggling to get it to run. I'm still getting errors in C bind. Education 3.n, not that one.
Well, are you just running this part? Or say when I ran this, I added in the DF $, because here we're going to add data equals DF at the end.
Okay. Probably is the issue. Thank you.
All right, so our DV, which is actually our DVs, is this C bind of our 3 separate DVs. And we're just going to regress that on achieve.f. And we'll tell it our data equals DF. And then we'll store that as a model. I'm going to call it mod.mv, for our multivariate model. And education. And so now we have our multivariate model put together. All right, so if we are looking at our collective DVs of education job sat 3 and job score 3 regressed on achieve.f, what is the research question that this model is asking or answering? Just as a reminder, this achieve.f, what does that variable represent?
Our IV.
Oh yeah, our independent variable, but how did we compute? What is that variable made of? the achievement score, which was computed based on
Yes, man, that's all right.
that math and reading achievement. So this is just people's junior high math and reading achievement levels, just categorized into low, low average, and high. So clearly we're trying to see what does the effect of, you know, students' junior high achievement, their math and reading achievement specifically, how does that relate to their final education, their job at the end of this line, and their job score at the end of this line, the job score and job satisfaction.
That was, it has to be a categorical variable for the multivariate.
Yes, for this particular way that we're analyzing it, yes. There are methods that you could use to use a continuous IV, but that's separate from what we're doing here. So yeah, our research question then, as we said, what it's answering is, you know, how does people's junior high achievement relate to their, you know, ultimate education, their levels of job satisfaction, and their job scores later in life, or are there differences in, you know, the outcome of these three things based on, you know, where their achievement was back when they were in junior high. All right, so then for the number 14, it says to provide the information from the macro assessment from the MANOVA and state what these results mean. So what we need is, we need now some sort of summary of our model. So for this, we will we'll use the summary function just like you would if you were running a linear model, where you make your model and then you say summary in that model. But the one difference is, well, two differences. One is that we have to tell it that this is a MANOVA model, because this, even though I called it mod MV, is technically not yet being analyzed as a MANOVA because it's still a linear model. So the distinction is kind of like the difference in running linear models versus running an ANOVA. And so what we'll do is we'll tell it summary and MANOVA mod.mv, and so this, putting that model inside MANOVA is what tells it, like, we want to analyze this as a MANOVA, not as a linear model. And then there are a few different tests that you can put in. On the homework, it specifically asks for Wilks lambda, so we'll tell it test equals, and then in quotation, Wilks. There are other options for this. I'll put this up here. There's the Peli's trace, Wilks lambda, Hotelling's T, and Roy's largest root. If you want to read more about what all these specific things do and when you might use one or the other, in the readings folder that I put on Box, there's discovery statistics with R, and the MANOVA chapter, you know, goes over all these real well. But in short, you know, Peli's trace is similar to R squared. Hotelling's T compares directly to the F ratio in an ANOVA. Wilks lambda, which is what we're looking at, is the amount of unexplained variance. Roy's largest root is like Hotelling's T, but it only looks for the first variant in the thing. But anyway, so like I said, if you want to read more into those, you can check out that chapter in that book. So when we run our summary, here's what it's going to put out for us. This is where we have our value of Wilks lambda, our approximate F, degrees of freedom, and our p-value down here. So if, like, let's for a moment, sorry, let me pull this up. So good? So let's for a moment imagine that we don't have three. This isn't a MANOVA. We're only looking at one thing, and it's an ANOVA. All right. So we run our ANOVA and we get our results with our F, our degrees of freedom, and our P. And we have like this 4 categorical variable, independent variable predicting some DV. And here's our information. What does this output tell you if it's an ANOVA?
That there is a significant difference.
There's a significant difference, right? And that's it. It's kind of like the omnibus ANOVA, that it doesn't tell you where the differences are. It just says like, yep, there's some sort of significant effect here. So what this tells you then is the same thing, only in a MANOVA sense, is that yes, there is some significant effect of this independent variable on these, a multivariate effect on these DVs. Do you want to?
No, one quick note. When you report your F, make sure to report both the effect degrees of freedom and the error degrees of freedom. There are a lot of people who seem to think that if you report MANOVA F, approximate F, you only report effect degrees of freedom. But you need to put 9,4449. And then just to echo what Austin is saying, what we have found here is that the 4 groups, our 4 achievement groups, differ on that linear combination of the 3 DVs. But we have no idea which groups differ and where in the DVs they might differ. All we know is they're not all the same.
And then in that problem on number 14, the next thing that it asks you for outside of verbally explaining this and putting in your actual inferential information, it also asks for partial eta squared and the magnitude of the effect. So to get partial eta squared, there's a function that's just called eta SQ, and this is from the HE plots package. And so if you just tell it eta squared and then put in your model, it will tell us that our partial eta squared is 0.066. If you look up, and the partial eta squared for MANOVA, if you look up like Cohen's like rules of thumb for what's small, medium, and large, you need to specifically look up the rules of thumb for MANOVA partial eta squared, because that'll be different than an ANOVA's rules of thumb. And if you look up one of those rules of thumb, do you happen to have?
I do. Yeah, so interpretation of your partial eta squared, if it's a 0.01, then we call that a small effect. If it's a 0.06, we would call that a medium effect. And a 0.14 would be considered large. And those come straight from Cohen's recommendations.
So in this case, what if our effect size is 0.066, then what is that magnitude of the effect?
Medium.
We got a medium effect here.
So let's pause. Did everybody have any trouble, or did anyone have any trouble running the MANOVA, getting the stuff?
I have a question. Is the PRF thing, is that the p-value for the?
Yeah, that's our
Okay.
p-value.
In scientific notation, which please don't include in your homework.
Oh, sorry. And that's so. If you're getting scientific notation and you hate it, one thing that I often do that is run. There's a command that I normally put it up at the top of my script, and I only didn't. Oh, there. So this options side pen equals 10. The side pen is scientific notation, and what this tells it is only use scientific notation if it's more than 10 decimal places. Like once it hits 10 decimal places, convert it to scientific notation. So you can try that. You'll still get that, but if I change my side pen to say 20 and run that, and now run that same effect size, or sorry, the model, like now it will actually give me the numbers. That options side pen equals whatever is how you set where you're cut off to convert to scientific notation.
But in this case, I also don't want 20 digits of P.
Less than 0.001.
Yes. And that comports with APA style. You'll see this in your homework assignments. Most of you did a great job with this. Most statistics should be reported to 2 decimal places. R's and P's should be reported to 3 decimal places. Also, R's and P's can never take a value greater than 1. Any statistic that can never take a value greater than 1 does not mean a leading 0 before the decimal. So, your APA pro tips of the day. So this would be fine for you to say just less than 0.001.
These are the 3
P's and R's are 3.
after this.
Yes, with no leading 0.
Cool. That's it, yeah.
Everything else, typically 2.
All right, so we all good on that?
So like when you report your approximate F, what are you going to report?
46.65.
All right. All right, so like we said, though, this just tells us that there is some difference in there somewhere, but we don't know where. We don't know on which things in this linear combination there are differences. So we have to do some follow-up tests to determine, how and where these groups actually differ. So that's going to bring us to our step-down analysis. So with our step-down analysis, we do a series of just linear models, just regular 1 dB at a time, essentially. And we'll do first we'll do an ANOVA with just the first dB, and we'll get to first, second, third here in a second. But we'll do the first dB regressed on our IV. The second model will be an ANCOVA, and all we're doing is we're putting the dB regressed on the second IV with the first IV added as a covariate. And then the third one will be the third dB regressed on the IV with both the first and second IVs as covariates. So basically what we want to do is we want to say, like, all right, we're going to pick one of our independent variables and see, does this have an effect on our dB? Yes, it does. Okay, now what about this second independent variable? If we control for the first variable, do we still have an effect of this second independent variable on our dependent variable? And then for our third one, we're saying, all right, so now with this third IV, does it have an effect on the dB after controlling for both the first and second? So that's why we're stepping down and we're saying, does this have an effect? Yes. Does it have an effect, or does this one have an effect if we control for this one? Yes. And then does the third one have an effect if we control for both of the first two? Now, in terms of the order in which you would put these in, it's really a theoretical question. In our case, if we're looking at total education, job score, and job satisfaction, it makes sense that the education that you get comes temporally before the job that you have or how satisfied you are with it, right? Does that make sense to everybody? And then as far as you have to have a job score, in order to be satisfied in that job. So it would make theoretical sense to have, that job score as your second variable. And then finally, after you have an education and a job, you'll have some level of satisfaction in that job or not. So what we want to do is we want to see, does achievement have an effect on education? Does job score have an effect, or does achievement have an effect on job score after controlling for education? And then does job satisfaction or achievement have an effect on job satisfaction after controlling for education and job score? Is that making sense?
So conceptually, let's think about this for a moment. And I'm going to do some, Mandy, can I borrow your drawer? Oh, thank you. Okay. Conceptually, what we're basically trying to do here is we're trying to say, if we have a reason to order our DBs, meaning we think there's a priority to them, like we talked about with dominoes, how we talked about how if you tip one over, then others should follow in a sequence. what we're trying to figure out here is when and where does your achievement in middle school matter later in life, okay? And so we could just say, does it matter for all the things? Does it matter for this? Does it matter for this? Does it matter for this? But because we think the things we're interested in are somehow ordered, that one, like your education ultimately tips where your job is likely to be, and what kind of job you have likely tips how satisfied you are, then we're really thinking about these as taking them in sequence. And so we have our achievement. That did not work at all. Awesome. So we have our achievement groups. Okay, and this is like what we're using to predict a whole series of DVs. The first DV we want to predict is the ultimate amount of education people get. Okay? And so we're going to basically trying to ask if this area of overlap is significant. Okay. Can I predict education from achievement? If I know how a middle schooler is doing, can I make some educated guess and be some more accurate than chance about how far they're going to go in school? Okay. Great, we're going to find that out in a moment. My next question is, okay, since I know that education is yoked to job score, which is basically from your data dictionary, it's a way of ranking the prestige of an occupation. So it's based on like a very long ranking, and I can't remember if they did this by experts or by lay persons, but people were listed like firefighters, teachers, janitors, professors, lawyers, doctors, whatever, veterinarians, and all these different things, and then said how prestigious, kind of rank how prestigious these jobs are. So you can see how they might be yoked to education, not entirely. They're also not entirely yoked to salary. Like teachers and nurses are really high up, and they'll compensate them with the prestige that we assign to that job. Okay. So our next question, after we answer this first one about whether middle school achievement helps us understand how far someone's going to get in life from an educational perspective, is, well, I know that's related to job score, but does achievement help me predict job score above and beyond what I could already predict based on just education? So it's like asking, our next question is looking at job score. And basically now the second model we're going to run is going to look at this piece and say, is this incrementally significantly improving my prediction? Okay. So that's what we mean by controlling for. Like after accounting for the fact that we know that there might be, or we think there might be differences in education, are there then differences in job score that could not be explained just by differences in education? And then finally, we'll add into that job sat. So our third model is going to basically look at this area and say, okay, after accounting for the fact that achievement may predict educational differences and maybe even predict job score or job prestige differences, can middle school education tell me something about how satisfied people are going to be with the jobs they ultimately have? That's a lot of pressure to put on middle schoolers who don't really need more pressure. Okay. But that's what we're going to find out. And that's why we're running these in a series of models. And when we say controlling for, what we really mean here is above and beyond what can be explained by this variable, or above and beyond what can be explained by these two variables. What is the incremental explanatory power of the following variable? Questions about that?
All right, so go ahead and make 3 linear models. The first model will be education regressed on achieve.f until your data is df. Our second one will be job score regressed on achievement.f plus the covariate of education3.n. And then our third model will be jobsat3.n regressed on achieve.f with the covariates of education3.n and job score 3. Now on these, like you could, if you wanted to, just do these one at a time. So create the first model and then answer the questions about the first model, and then, you know, down a couple numbers down the page, when you get to the part about the second model, type in, you know, the second model, and things like that. The way I like to work is whenever I have models that I have multiple similar models, I like to keep them together in my code. It just helps for me personally keep it more clear exactly what I'm doing. So that's completely personal preference stuff. And so that first summary that we looked at when we looked at Wilkes Lambda and stuff, remember that's that macro level assessment. And now we're getting into our mid-level assessment by doing these step-down procedures. So once you have your models put together, here it's asking, you know, for the information from the printout that would be informative for this, and so we're looking for our F, degrees of freedom, significance, and effect size. All we're going to do here is we're going to do an ANOVA and use the capital A ANOVA, which is the ANOVA from the CAR package. You'll find that there are multiple ANOVA functions. You know, AOV is one, lowercase ANOVA is another. The reason that we're going to use the capital A ANOVA from the CAR package is because it lets you specify what type of sum squares errors you're using. We're going to use type 3. And so all we have to do now is say ANOVA M1 type equals 3, and I think you can actually just use the number 3 too and not use I. This is just the way I do it, but anyway, so once we have we're doing our ANOVA on our first model, which again is just regressing education 3 in on achievement. So we're asking that first question. We're just looking at this area right here, and when we look down at our ANOVA summary, we can see, yeah, there's a significant effect of achievement in junior high on, you know, their ultimate education level. As far as the effect sizes, we'll use that same eta squared function. And we can see that our eta squared is 0.192. Now, this eta squared function, if you only have one predictor, then, you know, partial eta squared and eta squared are the exact same. Once you have multiple independent variables or covariates, then there's a difference between partial eta squared and eta squared. But this eta squared function outputs the partial eta squared for you. So when you do have multiple things in your model, it'll give you the partial eta squared for each one.
This is a large effect.
Yes.
Yeah, it's in 0.14 or greater would be meeting the criteria coincident for partial eta squared.
How do we get that magnitude of effect?
That's by looking at the chart and seeing, like, well, what is 0.19? Is that a small, medium, or large? The magnitude of effect is just asking, is that
In
small,
words.
medium, or large, you know, based on the conventional rules of thumb.
And increasingly, journal editors are asking me not just to report effect sizes, but actually to tell the reader what they are. Yeah, so I'm finding myself doing a lot more writing of, like, these were all in the medium to large range or whatever.
Right.
And I get it, because not everybody cares about stats, but and because there's a million of them, like an omega squared versus a partial eta versus eta versus B versus whatever, but It is helpful to actually use normal words to describe them.
It's pretty easy to find the reference though, because I do the same thing. Like if I'm reporting, whatever, I'll say, this is, typically conventionally considered a medium effect size, then throw in a site for, COA 1986 or whatever. And if you just Google effect size rules of thumb, there's like a CBU page that has like tons of different effect sizes, and it will have links to actual references and stuff that makes it really easy to find. For whichever effect size you're reporting, you can find a reference that gives some sort of guidance on what's small, medium, or large if you're going to go by a rule of thumb.
There are also great books on power analysis that have a lot of that information, and your textbook does include some information for the ones we're using. So what do we know now, guys? What do we know at this point?
Your middle school achievement has a large effect on your education level.
Do you know anything more than that? Very good. You don't know which groups, you don't know where, you just know that the 4 groups, somewhere among the 4 groups, there are differences in education or attainment in early adulthood. That's all you know. You don't know if it's group 1 compared to 4, you don't know if it's 1 compared to 2, if it's 3 compared, you don't know where it is.
So in order to do that, we want to look at our estimated marginal means. So to get into our estimated marginal means, we're going to use from the EM means package. There is a so load up that EM means package, and then the function is just called EM means, and we'll put in our object, which is our model. So we'll tell it M1, and then you tell it what variable you're wanting to get the estimated marginal means of. So achieve.f. And when we run this, we get our estimated marginal means, and I'm actually going to go ahead and the library is called EM means. And don't worry about copying and pasting over this plot stuff just yet, but basically I just wanted to show y'all what I did here is I took the output from this EM means and piped it into as data frame to make this read as a data frame, and pipe that straight into ggplot and use geom point range, which gives you a dot with lines going up and down. Told it my X is my achieve F categories, Y is EM mean, which is looking at the table 3.28, 3.71, et cetera. Then Y min and Y max is where you tell it how far the lines extend. Now, and notice here that I just put that the minimum is EM mean minus SE times 1.96. So it's literally just taking EM mean 3.28 plus 0.695 times, minus 0.0695 times 1.96. And then for Y max, it's SE times, or plus SE times 1.96. However, your standard error times 1.96 plus or minus is your confidence interval. So instead of using SE times 1.96, you could just say Y min equals lower.cl, Y max equals upper.cl. I just wanted to be sure to point out that your standard error times 1.96 is where your confidence intervals come from. So this SE times 1.96 is the exact same as your upper and lower confidence interval.
Okay, now I gotta explain this one a little bit more too. Can I hurry? Thank you. Okay. Can I use that part of the whiteboard? Okay. How many of you are familiar with the normal curve? If you took my fucking class, you better be familiar with the normal curve. Okay. What does the normal curve represent?
So, area where all the means fall underneath the distribution of means, and you resample the sample.
Yes. In most cases, it's like if you keep resampling and calculate a mean for a group, and then you put that sample back, resample again from a new, kind of randomly sample, and you plot all your means, what eventually you're going to get is what is the mean, and then kind of the mean of means, right? So, okay, but it represents sort of like where distribution falls. It's a theoretical distribution. If you fall right here, what does that mean from a z-score perspective?
0.
That means that your z-score is equal to 0. What is a z-score?
Distance from the mean in standard deviation units.
Yeah, z-score is a standard score, and the standard score is based on deviations, right, from standard deviation. So a z-score of 0 means that you don't deviate at all from the mean. You are the mean, okay? And that means your z-score is 0, which corresponds to 50th percentile, your right average, right? When you go up or down one standard deviation, what is your z-score?
1 or minus 1.
Yeah, so here the z is equal to -1, and here the z is equal to +1. These correspond with roughly what percentage of the population falls in here? Do you guys remember? Yeah, good. 68% total across these two bands. Okay, let's go out another standard deviation. If we're at -2 and +2, our z-scores are 2 and -2, right? What percentage of the population falls within these bands from -2 standard deviations to +2?
95, 96.
About 96%. So this area of the curve is 96% of people are going to score between -2 and +2, okay, from a standard deviation. So guess what z-score corresponds with 95% of the curve?
1.96.
1.96. So when we're creating all of this, what we're really telling R is that we want to plot the mean for that group plus or minus a confidence interval that encompasses 95% of the points. And 95% is based on this z distribution, okay? So if I don't go quite to 2, but I instead go to 1.96 plus and minus, I'm capturing 95% of the probable actual mean for that group. Like the real mean for that group, I have a point estimate. Like for this group, my point estimate of their achievement is 3.28. But of course, I'm not perfect. Tom tells me that all the time. He reminds me, I'm not perfect. I make mistakes. My mean could be off because I did sample, after all. I didn't actually test every middle schooler ever who was an immigrant. And so I'm 95% sure that the real achievement, educational achievement that these kids, or educational outcomes these kids have, is not exactly 3.28, but somewhere in the range of 3.15 to 3.42. And the way that I got that range was by using the normal curve. So when we just typed in the plot the points for each group, but we really do still need to compare each point to each other. And if you just have points, you can't tell who's significantly different from who else. But if you plot the point and the confidence interval, then you can tell. If the confidence intervals overlap, then you know those two groups are not significantly different from a p less than 0.05 or less than 5% chance, right? So that's what Austin did for us here. He basically helped us do a post hoc test for our significant ANOVA. We said we knew the groups differed on achievement in some way, but we didn't know where. So we could test it, like with a Tukey where you compare 1 to 2, 1 to 3, 1 to 4, 2 to 3, 2, and that's all fine, but we can also visualize it. To visualize it, we can plot the means, but you can't tell just by plotting means if things are different. You have to plot means and their confidence intervals. So that's what we did, and we used z-scores instead of just the minimum and max. We could have just done that. Austin could have saved us a lot of time. I made him do this by just saying, just plot the lower and the upper for every point. But I wanted you to understand what the lower and the upper fucking mean, okay? And what they mean is, from this distribution, I'm 95% sure, you know, that the mean is between this and this. That's how R got those values, and that's what we plotted. Make sense? Okay, good.
So then just as a reminder, this is how, again, to make it completely explicit, this is how you know that differences between each of these 4 groups is significant. You don't have overlapping confidence intervals. If, say, this low group, like the confidence interval was a little bit higher and this one was a little lower, and there was a little bit of overlap between the confidence intervals of these two, then you would say that there's not a significant difference between low and low average, but there is a significant difference between low average and high average, and a difference between high average and high, and then, of course, logically, you know, the difference between those other groups would be significant. But so just using those confidence intervals to be able to tell you whether or not differences between groups are significant.
So what do we have here, guys?
There's the Could you, theoretically, if you wanted to make your significance criteria more stringent, up that confidence interval
Absolutely.
calculation?
So consulting a z-table, if you want to be 99% sure, for example, if you consult a z-table, you find what is the z-score associated with 99% of the area under the curve, and instead of multiplying by 0.196, you multiply by what, it's like 2 point something, I don't remember what it is.
Cool.
Yeah, so you can absolutely do that.
All right, so that's the first step in our step-down procedure. So the second step is then looking at that second model that we entered. But before we look at that model, we have to look for the homogeneity of the regression slopes. And basically, all we have to do here is we have our model where, just as a reminder, our second model is, I'm on the wrong page, job score regressed on Achieve F plus Education 3. What we want to do is we want to change this to make this an interactive model. Instead of having education as a covariate, we want to let education interact with Achieve.F. If that interaction is significant, then that's going to tell you that, like, wait a second, there's significant differences depending on the level of this other thing, which tells you that that you don't have, you know, homogeneous regression slopes.
Can I pause it for a moment? What is, does anybody know what homogeneity regression slopes, what the assumption is? What does it mean?
The slopes are kind of all changing at the same rate.
The slopes of what are changing at the same?
The different IB groups.
Yeah. Basically, what we're wanting to know is that the adjustment that the Education 3 variable makes on the scores, on the job score, the amount that it adjusts, or the basically the slope, right, of how it adjusts, is the same in groups 1, 2, 3, and 4. So if it turns out that Education 3 adjusts scores more in, say, the high group than in, like, the low group, we have violated an assumption of a covariate. Every time you use ANCOVA, MANCOVA, anything where you're using a covariate, there's an implicit assumption that the covariate basically makes an adjustment to the original means that is similar in all groups. And I'm also going to, in a moment, ask you what is the difference between a mean and a marginal mean, which we're going to talk about too. This is all relevant because I want you to know what we're doing, not just like copy some code and then turn it into an assignment, but leave and feel like I have no fucking idea what those words were. I don't know what it all means. In order for us to do an ANCOVA, we have to make sure the adjustment is equivalent It might not be equivalent in magnitude, but at least sort of from a slope perspective. It is adjusting scores, controlling for things similarly across every group. If it's not, we cannot do any MANOVA. We have violated that assumption.
All right, so then here for number 18, like I said, to test this, all we're going to do is we're going to let these interact. So all I did is I copied and pasted the LM and then changed this plus sign to an asterisk, which now is letting achieve.f interact with education 3. Now there's one other thing that I want to show you for another way that you could do this using a thing called update. And I just wanted to show, because there are some cases where using this update is a more efficient way of doing things. And basically update is a way of saying like, hey, there's some object. In this case, our object is the second model, and we want to update it and change some of the information in it. So we're going to update model 2 in this period tilde period. That's saying like, leave the model as it is right now. Like, don't change anything on either side, or leave everything as it is. Then also add in this achieve.f colon education3.n. Whenever you are in linear models, this colon doesn't mean, it's not like select, where it's saying like select all the variables between these two things. This annotation is how it reads interactions. So when you just do achieve, in fact, let me just, if I run just the linear model here, you'll see that when we have achieve.f times education, it will give us all of those main effects, but then also it gives us these colons, which is how R is explicitly an interaction. So it automatically does that when you use the asterisk. You could say achieve.f plus education3.n plus achieve.f colon education3n, and that's saying the main effect of achieve, the main effect of education, and that interaction of these two. So by using this update, we're saying to update model 2, leave it as it is, but also add on that interaction that we're wanting to look at. These two things will output the exact same thing. I wanted to show you both because this update can be a very useful thing to know how to use, like when you're going through and doing a bunch of analyses and you're wanting to change models here and there to look at more nuanced things, but also sometimes, for instance, on our third step, adding that in, we'd have to add in, when we're looking at 3 or 2 covariates plus the IV, we would have to add on all the 2-way interactions plus the 3-way interaction manually. So in that case, it's quicker and easier just to copy and paste the whole thing, change the pluses to an asterisk, and call it a day. But anyway, so all we're doing here is, again, we're doing an ANOVA on our second model, but allowing that interaction. And all we're worried about is the interaction itself. We can see here this interaction is not significant, which is a good thing. Because again, if that interaction is significant, then that says like, well, the slope of this one thing depends on the level of the other, which is not what we want.
Sometimes you love moderation, you love to find that effects are different depending on whatever, but when you're doing these, you don't love moderation. So we're excited not to find a significant interaction.
So once we've ruled that out, we now know that we're not violating that assumption of homogeneity of regression slopes. And so now we can actually do that second part of our step-down procedure, which is exactly like the first, except for now we're going to use model 2 instead of model 1. So I'm just going to copy and paste up here, down to here, and change M1 to M2. And run both of these. So now, looking at our ANOVA of this second model, the second step-down procedure model, we can see the effect of the effect of pull up my model, I'm losing my train of thought here. The effect of achieve F is still significant even after controlling for is significant on job scores, on that job prestige level. There is a significant effect of achieve, even after controlling for the effect of education, which is also significant. So now looking at this part right here, this kind of solid part, we're saying, yep, that piece is still significant. Even once we've looked at this part is still significant. But again, you know, it doesn't really tell us where differences are. It's.
Can we talk about how significant? What is the magnitude of that?
Oh, yeah.
Can someone interpret? Maybe someone hasn't contributed yet today. Interpret.
Eta squared is like 0.05, so I guess it's a small, relatively small.
Yes. Exactly.
Y'all get that? And so then, as far as getting our, you know, estimated marginal means, you know, same thing as before. Well, only now we tell it we want the estimated marginal means of the second model. And now let's compare the
Austin, can you scroll up a little bit? I just missed your code.
where?
Okay, can we pause for a moment? Did everyone get their marginal means from the second part, right? We've done the first part, which was, did they differ on education? This part is model 1, right? We've now done the second part, model 2, which is the solid fill. Okay, and then in a moment we're going to do model 3, which is sort of our dotted fill. Okay. I want to talk a little bit about what the difference is between a mean and a marginal mean. Okay. Does anybody know what that difference is? Like,
Maybe.
yeah.
Like there's like the mean of the IB, like overall, right? And then there's the means of the individual like levels of that IB that are marginal.
Sorta.
Okay.
Sorta. Do me a quick favor. You have them both?
Yeah, here's our marginal means and our
Okay.
raw means.
Okay, so there's the difference. I think Austin just said the beautiful word, raw versus marginal. Okay, so if we had started off our very first data when we got our very first data, and we had divided up our groups into these 4 groups, and we said, what is the mean job score that each of these 4 groups? We just asked R to do that. We haven't done any analyses, whatever. We just said, what is the mean job score for these 4 achievement groups? And those numbers just appear at the bottom there. Can you read them out to me, please?
41.4, 43.9,
Whoops. 43.9,
46.4,
46.4,
48.5.
48.5. So on this, basically it goes, I think this thing goes from like 0 to 100. Basically, this is the low achieving group, low average, high achieving group. You can see that the job score increases with every group, right? And if we had just run an ANOVA, which we're going to get to at the end of our time, if we had just run an ANOVA, our ANOVA would have said, okay, well, how does group 1, or is there a difference in these means? And if so, where is the difference? Okay. So right now, the means are definitely different. You can see that they're different. We didn't run an ANOVA. What we did was we ran an ANCOVA. So we basically said these means, but adjusted for the differences the groups have in education. So a marginal mean is really an adjusted mean. It's like, okay, after partialing out the fact that the groups differed on education, what is their mean job score? And those marginal means, if you can read them out to me.
43.5, 45, 45.6, and 45.9.
Okay. So with our ANCOVA, these were the means that we were actually comparing. They were the mean job scores adjusting for or controlling for education. So it really did an ANOVA on these means. That's basically what ANCOVA did. It took the original means, it adjusted them because they were different on education. These are the adjusted means, and then it ANOVA'd this, basically. Okay? When you eyeball this, where do you think differences might be? I know we don't know confidence intervals and all that jazz, but for the moment, if you were to just sort of make a slightly educated guess.
Low and
Between low and high, anywhere else?
high. Low and the next to high?
Yeah, maybe low and everybody else, because these are all like within a point of each other, and this one is 1.5 points lower. We don't know the confidence intervals, all that shit. But for now, you can see like it kind of looks like, aside from the low group, these groups were all pretty similar once you controlled for education. Whereas originally we were like, oh yeah, like all the groups are really different, right? That's essentially what an ANCOVA is doing. Or any time that you do a regression where you control for something else, you're really basically saying, okay, well, it's almost like a handicap if any of you either golf or do bowling or anything where like you get scores added, points added or subtracted from your performance, because it's like, okay, well, we already know you guys are different in this way, but if I equate you based on that, how do you differ on this other thing? Okay. Yes?
Can you describe the controlling for education? Just like what does that, or either stats or just conceptually, what does that do?
Absolutely. Let me draw it. I'm going to try to draw this. I've actually never done this one before, but I'm going to make that shit up. Okay. By a normal curve. Can you run for me real quick the education mean differences among the groups?
Just the raw means.
Yeah. So we have 3.28, 3.71.
4.48.
Thank you.
5.22.
Okay. So we have plotted these out, and you know, like, group 1, 2, 3, 4, and this is education. And in our plot we had about here, and we had about here, and we had about here, and we had about here. Just like that plot that we just did, right up there, right? Okay, so what we're functionally doing when we adjust means on job score is we're basically saying, we know the groups differed in this way. We also know that education, in this case, education was significantly associated also with job score. We saw that in the F test that we just did. And it's basically saying, okay, you guys are all different, like you're all different heights. I get that, right? So for the next thing I'm gonna do, for the next task, I'm basically gonna try to make you all the same height. So for this group, you know, we're gonna basically kind of start off the next thing so that we're like, okay, you know, let's say for the moment that you're all kind of equal on this, or that at least I've controlled for it. Okay, so you're all on the same starting point. Now, how do you differ in your job score? And so that's functionally what we're doing. Now, of course, you can see that the absolute amount of adjustment is different by group, but the important thing is that regression slope, that the moderated, that the adjustment is not, it follows a kind of a linear, right, trend, so that we're adjusting at the low end similarly to how we're adjusting at the high end. So we basically make everybody equal at the next thing. Like, it didn't matter what place you came in on education, now we're all at the same starting line. How did you do on job score? And so that's the difference. Does that conceptually make more sense?
Yeah.
That's basically what we did. We said if we hadn't adjusted, we'd be just double counting basically that things were difficult for you, because job score is basically like conflating education and job score. So we don't want to conflate. We said, okay, let's equalize the groups now. We know you're different on education, but now if we make you all equal again, how do you differ on job score? And when we do the next one, we're going to say, okay, we're going to equate you guys now on this. Now how do you do on job sat? So each time it's like you're basically bringing the groups back to the same starting point, even if they were different at the end of the last sort of like analysis.
I guess I'm just thinking of like when you're writing this, like why is that important? Or like why, because you obviously can't like say, oh, we're all going to have the same educational attainment. So just I guess in terms of like actual
it has to do a lot with where you're going to try to intervene. So practically speaking, let's say in this case we found that education mattered and we found that job score mattered. Okay, but let's say that job score didn't matter, and then what we found, or let's take it even further, let's say we just did job satisfaction, and we found if we did an ANOVA, education mattered, an ANOVA, job satisfaction mattered. Somebody could take that and say, well, what we really need to do with these middle school kids is help them achieve more, right, get more education. Somebody else could say, well, what we really need to do with these middle school kids is help them feel better about their jobs. So we need to improve job satisfaction. But what we're trying to say is, well, wait a minute, right? Temporally speaking, education comes first. Do you really want to put your eggs into trying to help people feel better about their jobs? Or is your resource better spent on helping people get a better education? So we're saying, in this case, like, okay, education mattered. After controlling for that, did job score matter too? Okay. Because if it mattered too, then maybe we ought to also target some intervention in that direction. So it has a lot to do with that. So I think about it too the way I think about, like, for example, if a kid is misbehaving at school and you're trying to figure out what's the source of that misbehavior, like maybe you want to think about like where is the origin of this, and don't spend a lot of time trying to help the kid with like a math thing if the home environment is like I don't have food. Okay. So controlling for is really saying, does that matter? Great questions.
So we're probably going to have to finish up the last couple bits on Tuesday. I don't think we're going to have time, but we will go ahead and go through this one more part of it, and then I have a couple things I want to tell you about the homeworks from the first unit. And here I just did the same thing where I looked at those plots, and when she was talking about the means, she was saying, we don't know where the differences are, but again, like that's where you can look at your confidence intervals and see, like, okay, like the difference between this group and this group is not significant because those confidence intervals overlap. The confidence intervals of these overlap. Like really the only significant difference here is between the low and the high group specifically. But moving on to that third part of our step-down analysis, just like before we move on to actually assessing that third model that we made, we first need to check for that homogeneity of regression slopes, which is done how? Testing the model, but allowing the interactions. So we will do the same thing that we did before, only now we're going to have all three of our variables in the model. with interactions of, so this will give us the interaction of achieve F and education, education job score, and then the three-way interaction between all three. And when we run that, we can see, like down here, our interactions, and none of those is significant, which tells us what?
There is homogeneity of variant of slopes.
Yeah, we're in good standing here. And this is the one where I was telling you that using update would be kind of a pain, because you'd have to say update M3 period tilde period, and then add in achieve.f colon education 3.n plus achieve.f colon job score 3 plus education plus, and you'd have to add all of those in manually. So in this case, just copying and pasting and changing the plus signs to asterisks instead makes it a lot easier. But again, I just wanted to point out the update, because you may find yourself using that one day that's more efficient. Yeah, so that seems like a pretty good place to stop, and we'll finish up with the rest of the step down part 3 on Tuesday. As far as the homeworks go, I was looking through yesterday. There were a few spots that Anna wanted me to check, like scripts, and figure out, where things weren't lining up, where incorrect responses were coming from. The vast majority of them were simple transposition errors. Like when I ran your script, it shows me the correct value, but the value that you typed into your Word document was off. And so the only thing I can figure is that it was just a straight transposition error, and that was really the majority of the errors. The other thing that I saw a lot of was simply having things in the wrong order. So you would export some table and then copy and paste it into the thing, but the order of your variables in the table weren't the order of the variables in the Word document, which a few of you went ahead and just changed the things as well, but Anna's asking you to not do that, because that just makes it a pain in the ass to, when you're trying to go through and compare a bunch of people's, and now you're having to sort things out. So make sure whenever you are copying and pasting things like that, you have to pay attention to these things and make sure, like, okay, is my Excel sheet, my CSV that I wrote, is this in the right order? And if not, correct that before you copy and paste it over. And the third thing that that got a lot of people were using the wrong variables and not using the recoded variables specifically. So on, like, number 21, where we're looking at across all these different things, looking at these chi-squares and t-tests, they would use Father Ed instead of Father Ed recode and things like that. That was a very common problem. And then also that there was 2 or 3 that on that same part of doing our t-tests and chi-squares, looking at whether or not there's systematic variance in whether SMA and SRA are missing, that we're just using the wrong test. Just remember that a t-test is for a dichotomous thing. So you can't do a t-test with Father Ed because there's so many different groups of education there. That needs to be a chi-square. Some of you used t-tests on ones like, say, sex, which technically, if you're treating sex numerically and have 0 and 1, like, a t-test works. But if you have multiple groups, you have to use that chi-square, because t-test is just not appropriate in that case. But just those few things right there accounts for probably 98% of all the errors that I was looking at yesterday. So just be careful when you are transposing things from R into the other thing. And that's where during that first unit, some of the stuff I was doing as far as, like, you can sit here and type out all the things, and I was talking about putting them in the order that they're in the document to make it easier to copy and paste. You just really have to make sure to pay attention to those things. Otherwise, it just causes problems and headaches for everyone. Does anybody have any questions?
mostly, I mean, just, the homeworks were good. They were good. So these were very, very minor, like a point here, like that kind of stuff. And usually when I could tell, oh, you labeled this as father ed, but really this is, you know, education, then I would just relabel it for you. So wherever I could find that. But attention to detail doesn't matter. It takes me hours to grade all these, and it's okay. It took you hours to do them. But it just makes it easier if you can follow the Word document order. When I have a list of variables, the reason I put that list in there is that way it makes it much easier for me to just, you know, kind of go through. I actually start to memorize the numbers as I'm going through them, so it makes it, it's a little geeky and weird, but. So since Austin was checking on those couple of things for me, he just gave me everything back, so I should have those back for you later today or tomorrow. I'll update Blackboard, I'll hand them out to you probably in the grad suite things, but again, you'll have them before this next homework is due.
When was this next one due, on Tuesday?
No, because we're gonna still be doing this on Tuesday. So I wanna try to give you like some time between when we finish talking about it and when you need to turn it in. Especially because this homework and every homework from here on out is going to include a write-up of the results like you would write the results section of a manuscript. So you need to have time to do that. So my goal would be to give you a week between when you finish lab and when you would turn it in.
Do you have an example write-up?
There, the book has example write-ups for you. So I think the Tabashnik and Fidel has both. Here's some, well, they have SPSS and STATA, I think, or SAS scripts. But then in the end of every chapter, they show you how to write it up.
So could you send out the little script to make those plots?
To do what?
To make those plots?
Yeah. And then like as far as between now and Tuesday, like really and truly, step down part 3, spoiler alert, it's exactly like step down part 1 and step down part 2. And basically you could finish the rest of your homework up through, number 24. There's one more thing that we're going to cover, and then like your write-ups and stuff. So you could go ahead and knock out most of your homework and have it ready, before class next Tuesday. And it should take you no time to finish up that last little bit. Anything else?
Other questions? Stay safe. It's
Right on.
brutal today.
I love your show.